Welcome. Calculating limits algebraically is going to be the topic of today's lesson. And yeah, sure, last lesson we already discussed the limits, the idea behind the limit. We discussed how to find them graphically, estimate them from the table, yeah, and other stuff. We already introduced the infinite limits. Cool. However, we still don't have a tool to find them appropriately, yeah, to find them fast, quick, just pow pow pow, analytically. And so this is what we are going to do today. We're going to learn to evaluate limits properly. Of course, that will be much faster and much easier. All right, and we have to start with two basic limits. The limit of a constant. We have to start with the limit of the constant. So let's agree that the limit of a constant as x approaches a is a constant. You know why? Because constant always stays the same. That's a constant, right? So what's a constant on the graph? That's a horizontal line. And as we approach, as x gets closer to a, no matter what, right? It can be a, b, you can take any point at x-axis, any point. Your function will be always a constant. It doesn't care. Right here, the constant is the blue one. So it doesn't care. It's always a constant. So the limit of a constant is a constant, sure. The second important limit is the limit of the identity function. And basically, we discussed this type of limit previously, right? In fact, we work with straight lines. Nothing changes here. So if you take the limit of x as x approaches a, you'll get a. Very simple, right? You can take any point a, you'll get a. This is the value you approach both from the left and from the right. So very simple. Two basic limits. And now, if we also add up them with these 5 universal beautiful rules behind me, you will be able to evaluate lots and lots of limits. All right, so before these 5 rules, we need to introduce the beginning of this statement. Let's say, so first of all, we have just two functions, f of x and g of x. We have two functions. And of course, there is also a limit of a function f of x as x approaches a and it's equal to a. And the same thing for g of x, but it approaches different number b, of course, because there's different functions, two different functions. Okay, maybe they're equal, I don't know. But generally, different functions. And what's very important, but they approach the same value. Yeah, they get closer to the same value, a. X approaches a as x approaches a, f of x is a, and g of x is, okay, capital A, capital B, sure. And then, provided that, we can state 5 beautiful rules. So the first rule is the sum difference rule. And it says that if you want to find the limit now of the sum or difference of these two functions, f of x and g of x, you can just evaluate the limits separately and then add them up or subtract. And then you will get the answer. This is it. And again, all these rules, they can be proved, but we're not going to do it in this course. Of course, if you're really interested in, you have to check it out yourself. Yeah, because now the most important goal here is the only goal. I can say, of course, learning calculus is essential, but also the priority is, of course, to pass the exams. So all these rules are very easy to remember, and in fact, they're quite logical. So we're not going to prove them, but so here it is. This is how you do with sums and difference. The second one, the limit of a constant, right? So if you have a constant multiplied by your function, then you can just pull the constant out to the front and calculate your limit separately and then just multiply by a constant. Very easy. And in fact, again, if you really think about all these limits, all these rules, even graphically, or maybe you'll construct the tables, you'll actually understand that that's true. That's true, 100%. All right, the third rule is a product rule. So if you have, again, you want to evaluate the limit of a product of your function, f of x and g of x, again, you can evaluate separately limit of f of x, g of x, and then multiply them. The same thing works for the quotient, but of course, as usual, the only additional condition is that, of course, provided that b is not equal to 0. This is super important. Otherwise, yeah, it's something super weird. So b, of course, is not equal to 0. In this case, it works. And the fifth rule, and basically, so we call it power rule, but it's kind of root rule to if n lies somewhere between 0 and 1. So let's start with the power rule. So if you take the limit of f of x to some power, right, so to the power of n, then you can just evaluate the limit again, and then you find the power. Then you take the power of n, right? Then it will be just a to the n. This is it. Very simple. And of course, if n is greater than 0, greater than 1, I wouldn't even say 1. So if it's greater than 1, it's going to be just power rule, literally power rule, right? If it's 2, then yeah, you'll get a squared. If it's 3, you'll get a cubed, and so on. But if it's greater than 0 and less than 1, then it's going to be the root rule, in fact, right? Because, for example, if you get 1/2, if you take n 1/2, it's going to be a square root. That means that there is a square root, right? And you take a square root here, and so on. So basically, it's a power root slash square root. No, power rule slash root rule. That's all, right? So basically, it's like 5, 6 rules here, and these two basic limits. Now, if you really combine all this knowledge, you'll be able to evaluate any limit. And let's even kind of show you how to use it. So let's evaluate fast. Of course, then I will just remove it from here, everything, and then, but yeah, let's just simply evaluate the limit of this function. So basically, so we see that in fact we can apply here lots of rules. So this is how we should think about it. I can even say think about it. Of course, usually we are going to do it much faster in future, I guess even in a few minutes. But right now, you look at that and you have to understand, okay, I have to divide it into 3 pieces, into 3 different limits, because due to the first rule, yeah, sure, I have sum of 3 different functions. I can say x squared to x plus 1. So then I'm going to evaluate 3 different limits. The limit of a constant is going to be a constant. Good. So this one is finished. The limit of 2x, I'm going to use, in order to evaluate the limit of 2x, I'm going to use this second rule. I will pull the constant out to the front, and I will take the limit of x of identity function, and we know that's just a, right? So as x approaches 1 is going to be 1. Multiplied by 2 is going to be 2. Wonderful. And so these 2 limits are done. And now the last limit is going to be x squared. And I have to apply the power rule. So I have x squared. It means that I can evaluate the limit of x first, and then I'll just take the power. So it will be, again, it will be just 1, right? Limit of identity function is going to be 1 here. And then, of course, 1 squared is going to be 2. 1 squared is going to be 1. So it's going to be 1 plus 2. So the answer is 4. So this way, of course, now I will actually write it down again, but I will have to remove everything from the board. But I want you to think about it this way. In fact, right now, at least right now, this is how we do. This is how we apply the rules. Plus, because we already know, in fact, we're trying to break every limit down to these 2 limits, 2 simple limits, the limit of a constant and the limit of an identity function. And then, as we do so, we're going to use these 2 simplest, 2 basic limits in order to evaluate the limit, n plus rules, and we're going to get the answer. All right, now let me remove this from the board, and we will continue practicing. All right, so let's do it again. And let's write it down, let's do it step by step. So imagine want to evaluate the limit of x cubed plus x minus 1. I don't know. So let's take this function. Okay, x is not interesting, 7x. Cool. So what do we do now? We have to apply rule every rule, yes, step by step. So what is the first rule we apply? We apply the first rule, yeah, the sum rule, or sum difference rule. So it will be, we get three different limits. The limit as x approaches 1 of x cubed plus the limit of 7x, right, as x approaches 1, and minus the limit of a constant. Let's take, there was 1 before, let's take 3. Limit of 3. Yes, sure, so we have three different limits. Again, what is the limit of a constant? Very simple, that's just a constant, so it's going to be 3. This limit is done. Now we're interested in these two limits. If we really, let's actually just keep it here, and let's deal with this limit. Okay, let's just write it down as, so what's here? We need to apply the power rule, right? We see that. That's going to be the limit of x as x approaches 1 to the power of 3. So this is what it is if we apply the power rule. Wonderful. Next, here we apply constant rule. We bring the constant here. So constant is going to be at the front, and that will be the limit of x, identity function. And this is, okay, let's just rewrite it here again. But the main point is, what do we get now? This is now the simplest. Again, we just break it down into three basic limits: limit of a constant, limit of an identity function, limit of the identity function. So two identity functions and the limit of a constant. Very simple. So this is how you should at least think about it. And so what do we get? We get 1 plus 7 minus 3. Right, so we get 1 plus 7 minus 3. It's going to be 5. So the final answer is 5. So this is our limit, the limit of our function, x of the function x cubed plus 7x minus 3. Wonderful. Now the question is, all right, so this is the limit. And what's funny? Now try to substitute 1. What do we get? What do you get here? Try to substitute 1. You're going to get 1 plus 7 minus 3. You'll get exactly 5. Is that a shortcut? Is that some cheating? And actually it is. So the shortcut is direct substitution. The only question is, when does it work? And we kind of touched that previously. And in fact, it works every time when you have a continuous function. And all the rational functions, trigonometric functions, they're all continuous, right? So logarithmic functions, exponential functions, they're all continuous functions. So for them, it works. If you have a continuous function, direct substitution works every time. So yeah, sure, this is what happens behind the scenes, right? This is what happens for real. This is how we obtain the real value. But this is kind of the shortcut. Every time, instead of doing this, you can just substitute the number and you will get the answer. Super easy. And it works. It works. It really works. Again, of course, if your function is continuous. All right, now let's do one more example. Of course, now we'll solve a bunch of examples. The next one is going to be x squared minus 1 over x plus 3 as x approaches 2. Good. So we look at this limit and we recognize the quotient rule, right? So we're going to rewrite it as the limit, two different limits again. The limit of x squared minus 1 over as x approaches 2, yeah, and the limit as x approaches 2 of x plus 3. So we apply the quotient rule and we get this. Wonderful. So then we continue breaking down the limit and we have to apply more rules here. So we apply a constant, we apply the sum, the difference rule, then we get to difference. Okay, let's do it again. So it will be the limit of x squared minus the limit of 1 as x approaches 2, over the limit as x approaches 2. Here we have x, again just the sum rule. of 3. So this is what we get. Again, 4, and of course if we apply, let's actually just apply the power rule at once. Yeah, so we also apply the power rule. Then this is what we get. Again, we get 4 basic. Finally, eventually we get 4 basic limits. So, and the answer will be 4 minus 2. So let's write it down. It's going to be 4 minus 2. Oh, not, yeah, 2. Oh, no, 1. The limit of a constant, right? Just 1. I thought this is an identity function. 4 minus 1 over limit of an identity function, 2 plus the limit of a constant. 2 plus 3 over 2 plus 3. So the answer will be 3/5. So let's look what happens if we substitute 2 here. We're going to get 4 minus 1 over 2 plus 3, 5. Oh, so 5 in the denominator, 3 in the numerator. It's exactly the same answer. So from now on, I'm not going to write down all these steps every time. Basically, we're going to just use direct substitution. Because this is a shortcut, and of course writing down every time, all these things, there's no logic at all. So basically, if you have a, and we know that this, okay, this is some rational function, right? But basically, if the function is continuous, you'll be okay, you'll be fine. The direct substitution is going to work. And if it's not, then yeah, it's a different question. We'll now discuss the examples where it's not continuous. And so yeah, it needs some new tools, some new tricks now. And we'll of course learn them. Alright, so let's do a small recap. Basically, if you have a continuous function and all the polynomials, logarithmic functions, rationals, all these functions, they are continuous. And basically, for right now, we have to understand that continuous, it just means that you can sketch it without lifting your pencil, chalk, whatsoever. So if a function is continuous, and most of the functions we work with are continuous, okay, not all of them, of course, but polynomials, rational functions, logarithmic, exponential, all these functions, they are continuous, so it works. We can just do direct substitution, usually. Sometimes it doesn't work. And let's see the cases, let's work out the case where it doesn't work. For example, the function, actually, I guess we looked at similar limit in the first lesson. So imagine I want to evaluate this limit, right, of this function, x squared minus 9 divided by x minus 3. So what happens if I try direct substitution? So this is our, let's say, universal rule. First thing we're going to do every time, we're going to try direct substitution. So if it works, I'm not going to do anything else. Fine, I'll just get the answer. I try direct substitution, it works, good. It doesn't work, then yeah, we have to do something else. Now we'll discuss what can we do. Okay, so all right, so let's do a small recap. For any continuous function, right? And basically all the polynomials, rational functions, logarithmic, exponential, all these functions, basically they're continuous. And of course, generally for you right now at this moment of time, for you continuous means that you can sketch the graph without lifting your pencil. So this is what it means. It means that at least at some point, continuous at some point means that there is no breaks, holes or something strange. So this is just some simple line, right? And you can sketch it without lifting your pencil. It's continuous. So this is it. So if your function is continuous at this point, at some point, right? You can try direct substitution, and it will work out. But sometimes it's not continuous. Right? Sometimes there are some weird moments, and especially, so for example, like here. If you try, so we have a function x squared minus 9 divided by x minus 3. And by the word, I guess we looked at kind of similar limit in the first lesson. But anyway, so if you try to substitute 3, you will get 0 over 0. That's something weird, absolutely. So we call it indeterminate form. So for sure, it's not 0, believe me. 0 over 0 is not 0. And it's not 1 either. I don't know what's that. So you don't know too. And it's called indeterminate form. So it just means that direct substitution doesn't work. And we have to try something else. And in this case, we need to start doing some algebraic, non-trivial stuff, in fact. We have to try to do some tricks. And there's no calculus in here. In fact, you'll have to just apply your knowledge from algebra, try some different stuff to get to a point to simplify the limit, simplify the inner function, right? The function inside of the limit, to simplify it the way that then you can try direct substitution and it will work. So you have to get to a point where it will work. The direct substitution will work. So, and in order to get there, you have to do some algebra before. So let's do some algebra, and here it's actually very easy. We just have to factor the numerator, right? So we'll get x minus 3 multiplied by x plus 3 divided by x minus 3. Very simple. Now we can cancel out x minus 3 and we get the limit as x approaches 3 of x plus 3. And this is very simple limit. Yeah, this is the limit of a continuous function. Very simple, straight lines, 100% continuous. And you shouldn't even think about the continuity right now too much, because you just have to try the substitution. If it works, then yeah, you're fine. Just write down the answer. If it doesn't work, then yeah, sure, you have to do something. And here, of course, we tried direct substitution, and it works. 6. The answer is 6. Very simple. So even if you tried in the beginning and it didn't work out, all right, do some algebra, try to simplify the expression, and then try direct substitution again and get the answer. It doesn't work, again, simplify, and so on. So this is the rule. All right, next one. So what do we take now? What else interesting can we do? Imagine now, let me actually look at the example. So yeah, this is the example. And let's say x, right? So here we have x, I remember. Yeah, sure. So imagine this is the limit we want to evaluate. And of course, we try direct substitution first. We try it and we get 0 plus 4. Then we take the square root of 4. It will be 2. 2 minus 2, 0. And here we also have 0. So it's again 0 over 0. Indeterminate form. Again. So the direct substitution doesn't work. And we need to do something else. It means that we have to start doing some algebra again. And basically every time when you have a radical, the best move on the chessboard is going to multiply by... Okay, let's write it down. Somewhere nearby, multiply by the conjugate, right? Both numerator and the bottom, right? And the denominator. Multiply them both by the conjugate, and basically you multiply by 1. Yeah, so it doesn't change a thing. So you can do it easily. So if you take the limit of x plus 4, so let's rewrite it, minus 2 over x, and we multiply and divide by conjugate. So it's going to be the square root of x plus 4 plus 2 divided by x plus 4 square root of x plus 4 plus 2. Again, in fact we can say that we multiply by 1, so nothing changes, and we can do that. So basically then we get that the limit as x approaches 0 of, so we get, basically we get x plus 4 minus 4 divided by x, here x square root of x plus 4 minus 2 plus 2. Good. And so here at the top we see that we're going to get x. X plus 4 minus 4. This is just 4. This is just x. So basically it simplifies into the limit as x approaches 0 of x divided by x x plus 4 plus 2. Please tell me, what is the next step? You're right, direct substitution. Try direct substitution again. So we try to substitute 0. First, of course, we simplify, we cancel out x, and now this is why we actually did all this stuff, because now it really simplifies, and now this is our expression. So yeah, again, the question, what do we do next? We try direct substitution. Now we can try direct substitution now because we really changed something. Because of course, if we still keep here x and x, you substitute 0, you're going to get 0 over 0. So nothing changed. But now, now we canceled out x and we substitute 0, we're going to get 2 plus 2, and so 1 divided by 4. So this is going to be the answer, 1 over 4. And basically, yeah, this is what you should do every time when you have a radical. Usually, it means that you have to multiply by a conjugate and divide by a conjugate. So basically, multiply by 1. Yep. All right, now let's remove this from the board. Next examples. All right, so next example is going to be x squared multiplied by sine of 1 over x. And by the word, of course, generally. Now, every time when you see a limit, the first thing you do is direct substitution. You try to substitute your value and see what happens. If it works, perfect. This is the answer, right? Great. If it doesn't work, you try to simplify the expression, right? You do some algebra tricks and other stuff and things of the sort, and you try to simplify the expression so you take the direct substitution again and it works. No, you just wanna what the fuck. All right, so next example. Let's find the limit of x squared multiplied by sine of 1 over x as x approaches 0. And by the word, of course, generally now, every time when you see a limit, the first thing you do is direct substitution, right? You try to substitute. If it works, perfect. This is the answer. If it doesn't work, then sure, yeah, you need to work a bit. You need to simplify the expression in order to cancel out maybe something or something, and then try direct substitution, and usually you will get the answer this way. Maybe it won't work again. Then you have to simplify further, right? You go further and further and further and so on, so on, so on, so on, and you have to get to a point where you will simplify the way where substitution works. So this is the, let's say, ultimate rule. But here it doesn't really work, because look at this limit. You try direct substitution. We substitute 0. It will be 0 multiplied by sine of 1 over 0. What's that? This is super weird, right? So I don't know, it doesn't work, and I don't see an algebra tricks either, right? What am I going to do? Replace sine by cosine? What's the point? So it's kind of strange, and these type of limits require a new tool, a new method, and let me introduce you squeeze theorem or sandwich theorem. So imagine we have three functions: h of x, g of x, f of x, and there's a point C. Right, and for all x around this point, the following inequality holds. Right, so h of x is less than or equal to f of x, and f of x is less than or equal to g of x. And of course, it works for all x around C, except possibly at C itself. And we'll actually see that here it works too, because sometimes f of x will be undefined at point C. It can be undefined. So it's kind of, yeah, it doesn't work because f of x is undefined at point C. So around C, it works for 100%. And also, the second condition is that the limit of h of x is L, and the limit of g of x is L as x approaches C. So we have the same limit, right? They approach the same value as x approaches C. And then this theorem states that in this case, provided that, we can conclude that the limit of f of x as x approaches C is going to be also L. So this is it. This is the squeeze theorem. And you'll understand the name, the squeezed, the sandwich, when you look at the graph. Because usually it's about some oscillating functions and another subperiodic functions, right? So usually f of x is, so graphically we can write it down this way. For example, this is f of x. This is, let's say, g of x. Okay, let's make it. So this is g of x, and this is h of x. Yeah, my picture is not the best, unfortunately, but this is the point C. Right, so the point C, and the idea is, if you look at that, so yeah, sure, g of x, so this is g of x, yellow is g of x, let's actually write it down. Okay, so this is g of x, this is, the green one is h of x, and blue one is f of x. So for all x around C, we see that, yeah, g of x is greater than f of x, sure, and h of x is less than f of x for all x around. We see that, that's true. At points, so the first condition is true, great. The second, limit of h of x is L, right? So h of x approaches some number L at this point. Yeah, sure, a limit exists, we see. The limit of g of x also approaches the same value, L. So there's some point where they all intersect, yeah. And yeah, sure, then f of x has nothing to do but but also has the limit L. Nothing, it just squeezed. It's just literally squeezed. That's why it's squeeze theorem. There's an upper bread, there's a lower bread, and this is sausage, right? It's squeezed between these two tasty breads. At this point, then, yeah, it's gonna also have the limit L as x approaches C. Of course, the main point is that here, all these things are happening around point C. C is the main character here. C is important. So yeah, this way it works, and we can use the squeeze theorem. And now, how do we apply it here? Very easy. Let me remove that. So let's start. We start working with sine 1 over x, right? This is the most interesting part, in fact, here. Let's look at this function, sine of 1 over x. And what's beautiful about sines, cosines too, is that we know that for all x, for the entire domain, this inequality holds, right? This is true for the entire domain. Sine, the values of sine, the sign is less than 1 for all the time, and it's greater than -1. Sure, true. But it's kind of, I can't say even squeezed. It's not the time yet to use the word squeezed, but it's kind of, yeah, it's somewhere between all the time. This is the values of our function. That's true. So, okay, this is true. And of course, x is not equal to 0. It can't be. And what's then? Now, let's multiply by x squared. So we can then write down that negative x squared is less than sine x squared sine of 1 over x and less than x squared. So again, it doesn't change a thing, right? We just multiply by x squared the entire expression, the entire inequality. So yeah, it didn't change. So yeah, this is true too. Now then, let's also evaluate the limit, right? Let's take the limit of each term. Then take the limit, and we shouldn't even take the limit. What do I mean? So as you see, it's kind of the first condition, right? The first condition is done. So we have it. It's accomplished, right? We have, so it's kind of h of x is f of x, our function, and this is g of x. And as you see, this is the beginning of the squeeze theorem. And now, if we find the limit, if we evaluate the limit of h of x, which is negative x squared, of course, as x approaches 0, we're going to get 0. Sure. The same thing for the x squared. We will get 0. The limit exists and 0. This is the g of x. And then all these three conditions are true, right? We have them. We have all three conditions. First one, we have an inequality. We also see that negative x squared is 0. We also see that we also see that x squared is also 0. And it means that finally x squared multiplied by sine over 1 over x is squeezed. So the sausage will also, it means that the limit of, okay, I shouldn't even write it down. The sausage also, so the sausage is squeezed, and that's why the sausage is going to be equal to 0. So the answer is 0. We use the squeeze theorem as masters. So this way, you can also apply squeeze theorem and add it to your workshop. Yeah. Okay, so this way, you can use such a beautiful tool in order to evaluate these type of limits. So basically, yeah, it's usually about, it's really useful about, when you have some periodic function and other stuff. Yeah, if you look at that graphically, you will also see that it's true. Unfortunately, I don't really remember the way this thing looks. It's kind of weird, but 100% I remember that will be, no, I can't even say I remember, I'm sure we'll have, so what's negative x squared? That's a parabola. Positive x squared, that's also parabola, right? So we have two parabolas. Have two parabolas here. And yeah, let's look at x squared multiplied by sine of x. So it will be something, and so on. It's actually very, yeah, it was super logical. But the main point is that, so at point 1, and we consider these three functions at point 0, so this inequality holds. And as you see, it's kind of squeezed. It's literally squeezed, and our function is between these two functions around, so everything really true. So this way, we can find the final answer, 0. All right, so now we already evolved, right? Kind of evolved. So every time when you see limit, first you try direct substitution. Wonderful. So this is the first step. Second, if it doesn't work, you do some algebra, where you try to simplify your expression. Then you try direct substitution again. Sometimes you can use squeeze theorem. Wonderful. So what else? And actually, there are some special limits, let's say, that are essential, and they are to remember. So the first limit is called basic trigonometric limit. And it says that the limit as x approaches 0 of sine of x over x equals 1. And it's kind of non-trivial, because if you try direct substitution, you get 0 over 0. So that's why, of course, you can't kind of solve and evaluate the limit using the tricks, yeah, and the methods we discussed earlier. So you need something new, and you need basic trigonometric limit here. So if you want to evaluate this limit, you need basic trigonometric limit. So when you see these types of limit, you say, okay, this is 1, I know that. And yeah, unfortunately, you will have to remember this. You'll have to remember this formula. Okay, in fact, you can derive it, and we can do it using squeeze theorem again. However, no, I'm not going to do it, sorry. So this is the theorem to remember. Wonderful. Now let's just see how we can use it. Let's look at this limit. sine 5 of x divided by x. And you look at this limit and you think, oh, it's so close. I mean, look at this trigonometric limit. It's so close. But I don't see 5 here. If only there was a 5, I would just use the basic trigonometric limit and I would write 1. But there's no 5. But is that a problem? Of course not. Of course not. Just write down 5 here and multiply by 5, right? And nothing changes. Nothing changes because, in fact, you just multiply by 1. So you didn't change a thing. That's why, of course, you can write it down this way. And then you can pull the constant out to the front. So constant is going to be here. And you rewrite the limit as x approaches 0 of sine of 5x divided by 5x. So what's that? We see that this is basic trigonometric limit exactly. So this is equal to 1. And eventually 5 multiplied by 1 is 1. 5, of course. So the answer is 5. This way, and again, if you didn't know, imagine you didn't know the trigonometric limit, it would take a bunch of time. And I don't think you would even solve this limit. So the beginning was sine of 5x divided by x, right? So this was the beginning. Then we multiply by 5 and divide by 5. But it's not important. I mean, even look at this limit. You try the substitution, you get 0 over 0. And there's no, let's say, tricks to change it somehow, to try to simplify it, maybe cancel out something. There's no tricks, in fact, okay? No methods, nothing. So you need basic trigonometric limit in these cases. You need it. All right. Good. Let's solve one more example. Let me look at the example we want to solve. Yes, I see. So we want to evaluate this limit. 1 minus cosine of x divided by x. Yes, sir. Yes, I see. Absolutely. So again, of course, we start with the substitution. Every time the same thing. You substitute 0. You get 1 minus 1 divided by 0. So 0 over 0 one more time. That's really sad situation, but we know that there is a trigonometric limit. So the substitution doesn't work. And so we have to do something. We have to work with the expression now. Because it doesn't look like that still too. But if we somehow bring here cos sine, we'll be able to use the basic trigonometric limit. So what do? I suggest to multiply again by 1, but it will be like 1 plus cosine of x divided by 1 plus cosine of x. So it will be the limit as x approaches 0 of 1 minus cosine of x divided by x multiplied by 1 plus cosine of x divided by 1 plus cosine of x. So essentially we multiply by 1. And that's why, of course, they are equal, right? Good. But what do we get now at the top? Now we can write it down as limit as x approaches 0 of 1 minus cosine squared of x divided by x and multiply by 1 plus cosine of x. Fine. What's that? This is sine of x squared, right? Let me change this. All right, so this is 1 plus, this is sine squared of x. It's going to be 1 sine squared of x divided by, of course, we also have a limit, right? This is a mistake. All right, let me just say limit as x approaches 0. All right, so sine squared of x divided by x multiplied by 1 plus cosine of x. Good. So what happens now? What happens now? What happens now? And so what do? Let me check. Let me check. Now, if you write sine of x divided by x, sine squared of x. Now if we take sine of x and divide by x, we get 1. And then will be sine of x divided by, will it work? So 1. Yeah, absolutely. I already see the solution. So this is what we get. And yeah, it's pretty cool because now we can write it down as, where do we go? Let me remove this part. Let's remove this. All right, so it's in fact the same as limit as x approaches 0, sine of x divided by x, multiply by the limit. Yeah, we just split it up into two different limits. Of course, we also preserve multiplication, yeah, product here, and this is one of the properties of limits, so we can do it absolutely. Sine of x divided by x, multiply by limit as x approaches 0 of sine of x divided by x multiply 1 plus cosine of x. So this is it. What's that? We know that this is the basic trigonometric limit, so this is going to be 1. Wonderful. Now we look here, and it's kind of cool. Oh no, so x is here. This is what's beautiful. Yeah, x is here. So we just, in fact, separated it into two different limits, right? So here we have sine of x over x. Now we multiply by the limit of sine of x divided by 1 plus cosine of x. Wonderful. So this is 1. This is the basic trigonometric limit, the same thing. And this, now if it, and here in the second limit, we're going to try direct substitution. So we get 0 here. Bad beginning. But here we get 1 plus 1, 2, 0 over 2, 0. So we don't care. And this one is going to be 0. And we'll multiply 1 by 0, we get 0. Absolutely. So the answer is 0. This is the final answer, and it's 0. This is another way to use the basic trigonometric limit. And we couldn't get 0 in the beginning because x was, so we in the beginning we were getting 0 every time, right? 0 over 0, and it's in indeterminate form. 0 over 0 is not equal to 0. And here, after some tricks, simplifications, yeah, distributions, we, using trigonometric limit, separated limits the way we actually, in fact, we just, I can't say canceled out x, but we kind of dealt with it, so there's no x anymore. Yeah, so it's just, now x disappeared, this is beautiful, and now we get 1 multiplied by 0, so it's 0. Good. Now let's move on. Let's just move on. This is basic trigonometric limit. There's also one more limit, and we'll introduce it now with limits at infinity. We'll introduce it now. Yeah, absolutely. All right, so sometimes it happens, yeah, sometimes it's extremely important to observe the function at really large values of x. For example, again, let's refer back to the function f of x, 1 over x. And as we know, this is going to be the graph. Let me take blue. So this is the graph of our function. And what's interesting, imagine now I want to observe the behavior of our function when x is really great and really huge. And as we know, in fact, if you will scale the graph, if you will look at it, you know, in terms of really huge x, you will still see that this line there, it goes, but it never actually intersects with the x line, with the x-axis. So it will kind of get close to the x-axis, but it will never actually touch it. And the same thing here. Even as you increase x, yeah, it will get closer and closer and closer, but it will never actually touch the x-axis. So, and we're going to write it down this way. We're going to say that limit as x approaches infinity, for example, sometimes, or negative infinity, doesn't matter. So this just means that we want to observe what happens with the function, want to find what happens with the function when x grows, yeah, when we take really huge values of x. So for example, we go somewhere far after, I don't know, million, billion, trillion, so on. Look at the behavior of our function when x is super great, I mean super huge, and it really grows far away. So, and you have a function f of x here, I don't know, 1 over x. So in this case, as x approaches positive infinity, and it means somewhere there, very far away, when x is really huge, what is the value we approach? So in here, it's kind of our, as I told you, this line, it will go there for the infinity, for eternity, right? But it will never, so it will kind of go down and down and down and down, but it will never touch x-axis. It will never touch, but it will get closer and closer and closer every time. It will get really close to the line, but still it won't touch x-axis. And in this case, we're going to write it down that it actually kind of was the limit, and it's going to be 0. So it's like, yeah, our function, when if you take x really big and as we approach x to infinity, so as we increase the values of x and we go really far away, we'll see that our function heads towards 0. So it really tries to intersect x-axis, and kind of it gets super close, but it still, of course, doesn't intersect that. But this way we're going to denote it, yeah, with limit. So in fact, the same thing happens here. What's the answer when x of the limit as x approaches negative infinity, right? So we go this in this side, right? We'll look at the function here on the left side, and we try to think about x-axis, where about x value somewhere far away too. And we know that, yeah, function will slowly, step by step, right, it will kind of get closer to the line every time, to x-axis, but again, it won't actually touch it. So, of course, the limit, this is the value we approach, the values of your function approach, right? The values of the function f of x approach 0 as x approaches negative infinity, as x really, as we take x as really far away, really big axis, negative values, right? Really big negative values, it will try to go to 0, the function. So we're going to write it down 0 this way. So again, we're going to use, and we'll call it like limits at infinity. So sometimes it's just interesting to look at the behavior of a function at positive infinity, right, when you take x as really big, and at negative infinity when x is or negative, when you take big negative values. Yeah, great. You understand. So it's about that. And let's give more examples. For example, so of course generally limit as x approaches on a positive infinity of f of x equals L just means that as x approaches infinity, as you take really huge values here, as you go far away there at the positive to the positive side, f of x, it's kind of the difference between f of x and L is kind of arbitrarily small. So really, it gets really close to 0. Yeah, they're like the difference between f of x and L when x is really huge. It's very small, super small. And if it happens, then yeah, you will write it down this way. But what happens usually, and it happens all the time for polynomials, right? Imagine we have a polynomial. Any polynomial, eventually, let's take the easiest one, parabola, right? Eventually, what happens when you take huge x, right? If you look at the function and you grow your x values, what happens there? I mean, it just grows and grows and grows. What happens there when we look at the axis far away, somewhere there? I don't know. I mean, parabola will be, so you'll just, and it's not hard to evaluate the limit, right? Of course, I'm talking about the graphical method right now. You know, we just look at the graphs. But if you substitute infinity into your function, right, into your expression, what do you get? 1 over infinity. What's that? That's 0. The same thing here, right? You divide 1 over huge, like infinite huge number, you get 0, of course. So what happens when you look at the limit as x approaches infinity of x squared, right? So we have x squared here. What do you get? You get infinity, of course. Right? Infinity squared, infinity. So, and we see that from the graph. What happens somewhere there, right, where your x's are really huge? The function grows and grows somewhere, it moves to the top, to the moon, I don't know, to the Milky Way, right? It just flies far, far away too. So of course it's positive infinity there. And the same thing happens with every polynomial, every time. It can go to negative infinity, but every polynomial eventually will just rise, or rise up or down. It doesn't really matter. It can curve a bit somewhere here, but anyway it will go either up or down. So eventually, yeah, it will get some huge number. And this is it. So sometimes you will be interested in analysis of limits of functions, in fact, at infinity, or positive infinity or negative infinity. So, and there is even a theorem. You know, if we talk about the polynomials, by the way, there is a theorem. Rational, and it's not only about polynomials, it's about rationals. There is a theorem, rational theorem. Let's look at that. And in fact, I don't even want you to think about it as a theorem. In fact, this is some obvious fact. So every time, now look at this limit. So now we will work a bit with limits where x approaches infinity. So here we have some polynomial x squared plus 2x plus 1, let's say, and divide by x 2x cubed plus 3x plus 7. Imagine. So how do we get this? How do we evaluate this limit? If you just substitute infinity, you get infinity over infinity. This is indeterminate form. You can't do that, right? If you try direct substitution, it doesn't work. So again, we need some new trick, let's say. And the thing is that now we want to introduce the rational theorem, but I'll also show you a way to think about this type of limits without any theorems. This is just going to be some life hack. So let's start with the theorem. Okay, rational theorem. What does it say? It says that for limits where x approaches infinity, right, and you have a rational function, so some polynomial here divided by a polynomial here. So it's exactly what happens here. And so if you have this type of situation, this type of limit, and the theorem says that if the degree of the polynomial in the numerator, like it says that there are 3 different cases, 3 different situations, 3 different scenarios. So when m is larger than m, the degree of the polynomial in the numerator, the answer will be infinity. So if you take really huge x values, right, if you take really huge x, eventually your rational will just grow, right, also without any boundary, so it will be infinity. If m equals n, it says that the answer will be the ratio of the coefficients, so am and an. So let's say that generally qm is equal to an x to n plus an minus 1 x to n minus 1, and so on, right, to a1 multiplied by x and a0, I don't know, it's not super important. So oh, we have m, right, so we'll have m here, m, and so on. So and qn, the same thing, an so an is going to be am, and that's just leading coefficients, right? So this is going to be the ratio in case when m equals n. And if m is less than n, it will be 0. So 3 different cases. And okay, it works. So let's look at this theory. Let's look at this limit. So we look at the polynomials. We have two polynomials, so this rational function, wonderful. We have two polynomials. We look at the numerator. We see that the highest degree, right, the degree of the polynomial here is 2, right? So this is the highest exponent that we have. In the denominator, it's 3. So the degree in the denominator is 3. Here it's 2. So this is the third case. M is less than n, so it's going to be 0. So if the degree in the denominator is higher, then the degree in the numerator is going to be 0. If it's opposite situation, right? If here you have a higher degree and here, then it's going to be infinity. If they're equal, it will be just the ratio of coefficients in front of the leading terms. See. So this is it. But let me give you a life hack. So here it's 0. Okay, let's solve one more. Let me remove this. Or it's going to be life hack. So one more first. Now, if as limit as x approaches infinity of 7x cubed plus 2x squared plus x plus 4 divided by 13x squared plus 2x plus 1. Now, we look at the polynomial in the numerator. We see that the degree is 3. This is the highest exponent we have. Here it's 2. So m is so the degree is higher, right, in the numerator. And we see this is the first case. So it's going to be the infinity. Now let's kinda I can't even say proof, but understand, right, that this is super, in fact, clear and intuitive, this intuitive, clear idea. Because let's look at the rational function, right, as x approaches infinity. I can't even say approaches infinity. Let's just take some huge numbers and see what happens. Let's work with this rational. Okay, it's too huge. Let's look with this rational. So what happens in the numerator? Imagine we take x equals, so x 10. It will be 100 plus 20 plus 1, right? Here we have 2000 plus 30 plus 7. Okay, this is 10. And just already at 10, look at the numbers right here. It's 100 in comparison with 20 and 1. It's already kind of wins. The same thing here, 2000s, 30 and 7. There's already a huge difference between the numbers, right? And x is only 10. Now, take x equal to 1000, right? 1000. Now, let's try 1000. It will be 1,000,000 plus 2000s plus 1 divided by, here it will be literally billion to billions. I'm not going to use scientific notation, sorry. Plus 30, not 30. 3000 plus 7. 2 billions, 3007. Million, 2001. What's that? And this is only 1000. X equals 1000. And we approach x to infinity. So do you see the point? Now, what I'm saying, in fact, essentially, when you take really huge x, so when you have a limit and x approaches infinity, and you work with rationals, you shouldn't even, this is my life hack, right? You shouldn't even think about the theorem. Of course, it's cool if you remember the theorem, fine. But this is how I think. Every time when you see a rational, and I know that x approaches infinity, I think this way. Okay, my x values are huge. They're even greater than 1000. Even at 1000, the first term, right, with the highest exponent is absolutely different in comparison with all the others. So these two are nothing in comparison. These two are nothing in comparison with x cubed. These two are nothing in comparison with x squared. So In fact, I think about it this way every time. When you have, let's first of all deal with this one. Using my approach, my method. So we have a rational. Of course, I can say it's cool to write it down this way. You can, if someone wants you to prove it, right, maybe derive the answer, it's better to say that you use the rational theorem. But at least this way, you will remember it, okay? You won't lost in the theorem. So you won't say, okay, m is less than 1, and then the answer is infinity. So there will be no misunderstandings, because this way you will get the answer every time, and you will just then use the theorem when you already know the answer. So here's how I want you to think. And the numerator, you should have x squared. X squared plus 2x, again, so let's rewrite it first. 2x cubed plus 3x plus 7. So this is our rational, right? And we know, not 0, infinity, right? We approach it to infinity. It's super huge. And I already showed you that even at x 1000, this is super huge. This is also huge. And we can actually neglect these two terms, and the same thing here. And even if, okay, this is not full, right, not full polynomial, not standard one, there also should be some x squared. But even x squared, anyway, the leading term, right, with the highest exponent, anyway, it will be much bigger, much greater than any other terms of the polynomial. So every time when you have this situation, when x approaches infinity, you can look at that and you say, okay, x squared is super big. These two are nothing. I'm going to forget about them. Okay, this is just how I do it in my head. I just kind of, let's say, okay, it's approximately the limit as x approaches infinity. Approximately. Now I can just write down x squared. Because 2x and plus 1, they don't really play a huge role here. I don't care about that. The same thing here. I look at the denominator. I say, okay, 2x cubed. This is what's really interesting. 2x cubed is really essential. And 3x and plus 7, no, I don't care. They are small. 2x cubed, this is a really huge number. And they are, okay, I don't care. That's why we kind of use approximate. Approximately, this is true. And now we work with this. So what do we have? Very simple situation. Now we can cancel out x squared, and we get the limit as x approaches infinity, 1 divided by 2x. So what's that? It's 1 divided by infinity, that's 0. So the answer is 0. This way you can easily get the correct answer. And then if someone asks you, so instead of writing this, right, because it's not super, nobody teaches this way on for AP for college board, okay, so it's not super correct. And if you write it down this way, you can just write down that it's equal to 0 from the beginning, like x squared plus 2x divided by this equals to 0, because due to the rational theorem, because the m is less than n, right? The order of the polynomial in the numerator is higher than in the denominator, and that's all. But this is just how you get the answer in your head. You shouldn't even remember the rational theorem. You just do it this way, you get the answer, you know it's 0, and then you say, yeah, due to rational theorem, this is 0. Because, no, m is less than n, that's all. But now you don't really remember the rational theorem, you just say it. You first get the answer and you say, yeah, I just use rational theorem. But this is the life hack, how to get the answer first. You get the answer and then you say, yeah, I used rational theorem. Like, no questions, I used rational theorem. And they'll say, okay, this is true, it's absolutely true. So this way you can approach the problem, these types of limits. And let's look at this limit. The same thing, this is the trick because it's super fast. You look at the limit. Okay, you say x is huge. So basically, I don't care about that. I don't care about this. So essentially, I can say that this limit is approximately, so you do it in your head, right? This limit is approximately the limit as x approaches infinity, 7x cubed divided by 13x squared. Approximately, this is it, because this is really huge as x approaches infinity in comparison with all the other terms. So we can neglect these two terms and all the other three terms too, so these three numbers. So we don't care about that. We get 7x cubed divided by 13x squared. So we cancel out x squared and we get 7x divided by 13. And of course, x approaches infinity just means that we will get infinity. So the answer is infinity. And indeed, if you apply the rational theorem, you see that, yeah, m is larger than n is going to be infinity. But this way, you shouldn't remember the theorem. You will just say, yeah, due to a rational theorem, it's infinity. No questions. But I don't remember this stuff. I just look at that, the number, I look at the problem this way, and I see that, yeah, it's infinity, due to rational theorem. No questions. So, and let's do one more, and then we'll also show one very interesting limit here. And now I'll have to wash normally and properly the entire board. So let's now try to solve this limit. Let's take negative infinity. It's not really important. Anyway, it's a huge number, right? We don't care. So we take negative infinity as x of x, let's see, to the fourth plus 3x cubed minus x plus 21, and divided by 4x cubed plus 7x cubed, 4x to the fourth plus 7x cubed minus 2x plus 1 minus 2x squared. Let's see. It doesn't matter. Now we look at this, and again we apply this type of thinking, right? We see, okay, x, we approach some huge number, even if it's negative, I don't care. We approach huge number, so in fact we can neglect all the other terms here, we don't care, and we can only think about x to the fourth and 4x to the fourth. So we get then that this is approximately, again you do it in your head, this is x cubed, x to the fourth divided by 4x to the fourth. And yes, so x to the fourth is much greater than anything else, and 4x to the fourth is much greater than anything else in the denominator. So approximately it's equal to x to the fourth divided by 4x to the fourth. So we can cancel out x to the fourth and we get 1/4. So this is the answer, right? You cancel out x, there is no x anymore. 1/4. The answer is 1/4. And if we look at the theorem and you say due to rational theorem, but now if we look at the theorem, you'll see that absolutely this is true, because the degree in the denominator and the numerator, right, they are equal. The degree is the same. It's 4. It's 4. So m equals n, and then is going to be the ratio of the leading coefficients. So here the coefficient is 1, right? Here is 4. 1/4. Absolutely. So this is it. This is how, that's why every time when you see a limit where x approaches infinity, it's going to be easy. Especially if it's rational. It's going to be super easy. Very easy. And there is one more interesting limit, I can say. Now we will remove everything from the board and we'll kind of touch it too. And then we'll finish for today. It will be enough for today. Alright, so one more way to look at this. In fact, you know, this is the third one. So it's so easy. Every time you have a rational and x approaches infinity, it's going to be easy, I guarantee you. I'm giving you the third method, right, to look at the problem, to approach the problem. So we have a limit. Here we have 2x squared plus 1 divided by x cubed plus 2x plus, 2x squared plus 7x plus 4. The third method. Now imagine you forgot the rational theorem. You forgot the things I've told you, you know, this approximation. You now can do one more trick. You can divide both numerator and denominator by the x with the highest exponent. So you find the highest exponent in the entire expression. You see, okay, that's x cubed. And you say, okay, let me divide both numerator and denominator by x cubed. And because you divide both of them, nothing changes again. Because basically, you just multiply by one more time. So what again, so it's equivalent, right? It's equal. It's going to be equal expression. So now we get the limit as x approaches infinity. So it's another approach. You look at the expression and you find x with the highest exponent. You see x cubed. Okay, let me divide by x cubed. So you say, let me divide by x cubed both numerator and denominator. x cubed. Let's even, okay, let's write it down this way first. Now you look at the numerator. Okay, let's write it down this way. Yeah, let's distribute it a bit. So it will be 1 over x, okay, 2 over x plus 1 over x cubed in the numerator, and in the denominator you'll have 1 plus 2 over x, right? So we divide every term by x cubed. 1 plus 2 divided by x plus 7 divided by x squared plus 4 divided by x cubed. And now you just remember. Now you say, let me try direct substitution, right? You substitute infinity everywhere. 2 divided by infinity, 0. 1 divided by infinity, 0. So this is 0, this is 0. 0, 0. We go here, we move here. 1 plus, this is 0, this is 0, this is also 0. So eventually you get 1 over 0. What's that? That's 0. So the answer is 0. This way. You can approach the problem this way too. And let's now remember rational theorem, for example. We look at the expression. Let's check if the answer is true, is correct. So we look at the numerator, the highest order, so the order of our polynomial is 2. Here it's 3, the degree of the polynomial. It's 2, here is 3. So yes, absolutely. The degree in the denominator is higher. It means that we will get 0 by the rational theorem. Or we also remember the things I've told you, right? The approximation. So it's approximately 2x squared divided by x cubed. So it's basically 2 divided by x. And that's 0. So you can approach these type of limits in any way, but you will get the right answer. So I gave you 3 different methods. Choose whatever you want and use it. That's all. So rational theory, every time when you have a rational and there's x going to infinity, that will be super easy, super easy. All right, and so now when we talked about the x approaching infinity, negative infinity, it doesn't matter. So when x is sufficiently large, there's also one more limit to add here. So I told you about the basic trigonometry limit, yes, so it's the limit when x approaches 0. Some limit to remember. So one more limit to remember is going to be the second one. Yeah, the second limit to remember is going to be, in fact, the definition of the number e. We can define number e this way. So when x approaches infinity, limit as x approaches infinity of 1 plus 1 over x to the power of x. And this is going to be e. So when you see this type of limit, it's equal to e. Okay, this is very, again, I can't say it's super simple, but you have to remember this limit. This is second limit to remember. This is the definition of e. And plus, so if here you'll have not 1, but any other number, I don't know, so as x approaches infinity, of 1 plus, I don't know, 7x to the x, it's going to be e. Okay, let's write it down, not 7a, yeah? Let's choose a. So it's going to be e to the a. Yes, so this is it. Basically, now let's, I don't know, solve one more, one example. It will be, so let's solve the limit as x approaches infinity of 1 plus 7x to the x multiplied by sine of 7x divided by x. Yeah, let's look at this limit. Let me remove this. I hope you already remembered the limit. So this is the situation. Imagine we want to evaluate this limit. So what happens? We substitute infinity and we get some super strange situation, 1 to infinity. And that's not 1. This is indeterminate form. And here, this is also super weird thing. So this thing is undefined in infinity, right? It oscillates. So it doesn't work this way. Okay, sorry. Bad example. We remove sine, so it's not 0, right? Bad example. Okay, I wanted to combine 2 limits, but it didn't work out. All right, we just solve this. For example, you get this limit. So You see this limit, what's the answer? The answer is e to the 7. Very simple. Because, as we discussed, this is one of the limits to remember. So 1, basic trigonometric limit, right? Let's write it down one more time. Limit of sine of x as x approaches over x as x approaches 0. This is 1. And the second limit is the limit as x approaches infinity of 1 plus, it's better to remember it this way, yeah, generally, when there is some number. If it's 1, it's going to be e to the 1, right? So it's e to the a. And if it's 1, it's 1. If it's 7, it's 7. So it's here, it's 7. It's going to be 7. It's 3, 3. So this type of limit is e to the power of this number. That's it. Basically, this is all. Right now, you already know a lot about limits. Of course, you will gain one more super cool skill, essential tool, L'Hopital's rule, but a bit later. But even now, you can, in fact, you evaluate a lot of and a bunch of limits, existing limits. So if you have a limit where x approaches some number, but generally, when you have a limit, first thing you do is direct substitution. Then it depends on the situation. If x approaches finite number, right, some 0, any other finite number, you will try some algebra. As you know, you can try to look at the basic trigonometric limit if it's 0, squeeze theorem, and so this stuff. If it's infinity, usually it can be rational theorem, rationals, right? With rationals we already discussed, it's super easy. It can be this limit, it can be definition of number e, and this is it, basically. Right now, this is all your knowledge. And again, in fact, calculus is very easy. It all comes down to algebra every time, every single time. All right, this is all for today. This is all for lesson number 2. Happy studying. Happy studying. Really, I hope you will practice a lot. You have to practice a lot. And yeah, and everything will be fine. If you have some questions, ask them. And see you in the next lesson. Smash AP.